Hi everybody. We are going to do 922 together via these video notes. So it's definitely a little different from what we're used to, but I'm going to ask that you all listen and follow along. Try your best to stay mentally engaged in this so that the outcome of learning what I hope you'll learn happens even though I'm not here with you. So what I need for you right now, if you haven't done so already, is make sure everybody has this 922 worksheet in front of them that you're seeing on this screen, and we're going to work through this together. So starting with 105, does the general equation y equals a sine of x minus h plus k allow for every possible transformation of the graph of sine of x? So I'm going to stop right there and remind you guys last class what we saw with sine of x is that we can transform that function or move it around or stretch it or shift it just like we can any other equation that we did with parent functions earlier. So we know that the a out front we saw from last class stretches that it increases or shortens the altitude, the height of the function. We know that the minus h is a horizontal shift right or left, and the plus k is a vertical shift up or down. So to continue this question, are there any other transformations other than those produced by changing A, H, and K? Think back to the graphs you made for the swinging bag of blood activity. Discuss with your team. Be prepared to share. So at this point, I would like you to pause or even just talk as a class. And you may have gathered by now there is one more thing we can do to affect the graph of the sine function. I'd like you to pause, chat about it. What else can we do to physically change the sine graph? Okay, hopefully you chatted and at least shared a few ideas. So I know this is strange since I'm not there and I can't hear your ideas, but what I'm hoping or expecting to have come up was that, let me graph a regular sine function. So positive one here, negative one here. And let's say this is 2 pi. So we could have a normal sine function. The one thing we have not talked about is taking that normal sine function and changing the period of it, which is how quickly or slowly it repeats. So a sine function could kind of be squished together horizontally like that, or it could be stretched out horizontally like this. So we just haven't really explored that with the sine equation yet. So that's what we're going to look at today. So we're going to jump into problem 106. If you have your book, now would be a good time to open up to page 466. And you can read along with me. I'm stalling because I know you're all opening your books right now. Okay, so I'm going to read through 106. Try and pay attention. Read along with me. All right, it's called the radar screen. Brianna is an air traffic controller. Every day she watches the radar line, like a 1-unit radius of a circle, go around her screen time after time. On one particularly slow travel day, Brianna noticed that it takes approximately 2 seconds for the radar line to travel through an angle of pi 6 radians. She decides to make a graph in which the input is time and the output is distance from the outward end of the radar line to the horizontal axis. Okay, so let's stop right there and repeat some of those important pieces of information. So she's looking at this radar line. We've got the screen right here. And she found out that it takes 2 seconds. So 2 seconds for the line to travel an angle of pi 6 radians. So that's kind of like our rate of change. We can think of it like how quickly this line is moving. Then let's think about the table and graph she's making. So the input is time. So we would have time up here we see on this table right here. The output is the distance from the end of the radar line to the horizontal axis. The end of the radar line is right here. The horizontal axis is straight down. We know that that vertical distance to the horizontal axis is the sine function. So what we see here are our 2 columns, our input, time, our output, that vertical distance, which is sine of theta. So nothing is new. We're just adding in this new thing about time being introduced in here instead of the angle measure. So time is our input, so I'll put an X there. Our output is Y sine of theta, or sine of X. So we're going to fill in this table and graph this relationship that she's noticing. So if you look at our table, after 0 seconds, theta is still 0. The sine of 0 is 0. So what I want you guys to do right now is pause the video and get out your unit circles. We are going to need the unit circles. Like I said, we rely heavily on those. Pause now, get them out so that you can quickly reference them. Okay, so to fill in this table, let's go from time in seconds to the value of theta. It's important to understand what we were told, that every 2 seconds, the value of theta increases by pi over 6. So 4 seconds later, pi over 6 has increased by another pi over 6, so it would actually be at 2 pi over 6. But we can simplify that to pi thirds. So after 6 seconds, we've got another pi over 6. So this is 1 pi over 6, 2 pi over 6. This next one would be 3 pi over 6. That's the angle rotation. And sorry, you can tell it's hard for me to write on this. 3 pi over 6. I'm going to continue just adding up in terms of pi over 6, and then we'll simplify. 4 pi over 6, 5 pi over 6, 6 pi over 6, which is just pi, and 7 pi over 6. Okay, now we can simplify these. So 5, let's see. After 6 seconds, we were at 3 pi over 6, that's pi over 2. 4 pi over 6 is 2 pi thirds. 5 pi over 6 is simplified, pi is simplified, and so is 7 pi over 6. Okay, so we are using this rate that theta is changing, and now we can calculate the sine at each value of theta, but this is based on seconds, remember. So the sine of theta, now you should be looking at your unit circle and filling in the sine of each of these rotations. So that means, again, we're not computing anything. Now that we went through the work of forming our unit circle, all you're looking at now are the y values for each of these radian rotations. So we're going to fill those in. All right, the sine of pi over 6, we look at the y value on our unit circle, get 1/2. Sine of pi thirds, looking at our unit circle, we get root 3 over 2. Since we're going to be graphing this, the decimal value of that will be useful, so that would be 0.866. Sine of pi halves is 1, top of the unit circle. Sine of 2 pi thirds is root 3 over 2 again, 0.866. Sine of 5 pi over 6 is 1/2. Sine of pi, we're at 0. And at 7 pi over 6, the sine is negative 1/2. So what we've just filled in our table is the vertical height. These are all the vertical heights based on this number of seconds that have passed on the radar screen. So now we're going to take each of these ordered pairs. Remember, this first column is input along the x-axis, and this last column is the output, the y-axis. So at 0 seconds, we're at 0. So start filling in the actual graph now. At 2 seconds, we're at 1/2. At 4 seconds, 0.866. At 6 seconds, it's at 1. 8 seconds, 0.866. 10 seconds, 1/2. 12 seconds, 0. And 14 seconds, negative 1/2. Okay. So what we see here is the first several seconds of the radar screen. We will continue to see that moving on as well. So let's take a look and think about this next question. How is this graph different from similar sine graphs that we've made? So the first thing I'm hoping you guys see here is that the shape of the graph overall, yes, looks the same. But if you remember the other sine graphs we've made, those start repeating at 2 pi, where this sine graph, so this is what a typical sine graph looks like. 2 pi is about 6.2. We see this sine graph is not even, this graph is only halfway through its cycle at 12 seconds. So one big change here is that the x-axis isn't even in terms of angle measurement anymore. We were talking about seconds. So the x-axis measures time. That's one change. And not angle. Another big change here is just when we see this sine function repeat is not at the normal 2 pi. We see that it will not follow that, so and then we'll specify how. So this does not follow the same pattern. Of the length of it, of the sine function. Now let's talk about how long it does take to complete one full revolution of the radar line. So how can we see how long that will take from our graph? Looking at the graph, we see half of this rotation at 12 seconds, which indicates that another 12 seconds later, that radar line, so again, think of this as representing the height of the radar line. It's positive, and then it switches back down to negative, and you should be able to understand that by thinking about this height. I'm going to map it out for you right here. It's positive, and then it's negative, and then it starts to cycle over again. So we see right here at this 12-second mark, we're halfway through. So out here at 24, it will repeat again. So this one, how long does it complete to take one full revolution? That would be 24 seconds. And we know that because we can just visually see that on the graph. It was halfway through at 12 seconds, which means it'll be completely through at 24 seconds. All right, let's turn the page over and answer a few more questions and get to the main focus of this problem. Okay, so revisiting the general equation for a transformation on sine of x, we have the a out front, x minus h inside, and the plus k. Those values, a, h, and k, are called parameters, and we discussed this a little bit with our other parent functions when we talked about changing those values. One question we want to think about is where can a new parameter be introduced in here that would stretch out or compress this function horizontally. So we already know that this a value stretches the sine graph vertically. How could we change this by adding a number somewhere that would change it horizontally? So in order to do that, think about which variable represents horizontal movement here, and that would be x. So the answer to this one is introducing some sort of number out in front of x, a parameter in front of x. And we'll kind of explore what numbers in front of x will actually do to these graphs. All right, so now we're going to investigate in part B how changing the number in front of x will work. Use your graphing calculator to test the result of putting this new parameter into your general equation. What happens when it gets larger? What happens when it gets smaller? So here's what I'm talking about, and I'll show you a video of my calculator. We are talking about instead of just sine of x, what if it was the sine of 2x? So we haven't seen any equations like that yet. What if it was the sine of 1/2 x? How are these going to affect the graph? So let's take a look and see. Okay, I'm going to do my best to hold this still and show you guys at least a chance to see how this is going to affect our graph. So if you can see in my first line, I've got y equals the sine of x. What I'm going to do is enter a couple more. So I'm just having sine of x plain just so I have that baseline. I'm going to do one that's sine of 2x just to see what happens there. Maybe even I'll skip down in purple. We can do sine of 3x. See what happens with that. And then we'll look again. And I'm actually going to go smaller now, something less than 1 out in front of x. So we will do sine of, let's do like 0.5x. Okay, so these are going to be graphed in those orders. So we'll see regular sine in blue. The next one will be sine of 2x. The next one will be sine of 3x. And the last one will be sine of 1/2 x. So keep that in mind as these graphs populate the screen. Another thing I want to remind you is of the window and the mode. So keep looking here. I'm going to show you. I'm in radian mode. So think about what that means in terms of my window. I made my x max 2 pi because I'm in radian mode, and I know that at 2 pi that's 360 degrees. Okay, so let's go back. These are the functions we're graphing, and let's take a look at the graph. So here's sine of x. This should look familiar, ending at 2 pi, or repeating at 2 pi. Here we have sine of 2x. Here we have sine of 3x. And this is sine of 0.5x. So think about what those numbers increasing and decreasing did with the number of times we saw that sine function actually populate in this one window from 0 to 2 pi. Okay, so I'm just going to slide that up there. And we've already seen the examples on this screen, so we can move on to the next one. So now let's think about a general equation for the sine function that talks about that new parameter. So I'm going to write our final transformation on the sine function equation. So this is going to be y equals the a, which we already knew, would stretch it vertically. Then we have sine, and these numbers that go in front, this is going to seem a little confusing. We'll use the letter b for those numbers. And then in parentheses, it's x minus h, and then plus k. So the way this always works is that new parameter that will stretch it horizontally is actually on the outside of the x minus h, and you can think of it as 2 sets of parentheses if that makes a little more sense to you. So in a few minutes we'll look at 9.2.3, and we will learn more specifically exactly how to figure out what b does to the graph. All right, so just for a little bit of practice down here in number 9108, so what we've been looking at is the period of the sine function, and the period represents when the sine function starts repeating the same pattern. So basically one full round through the sine function, how long that takes. So that would be called the period. So in parts A, B, C, and D here, we're just going to talk about the period based on the description or the graph. So looking at part A, we're looking at a sine function, and we see right here at pi, that's where it starts to repeat. So in this case, the period is pi, even though typically the sine function has a period of 2 pi, which we'll get to in a second. Part B, a pendulum takes 3 seconds to complete one cycle. So that would mean the period of that pendulum is 3 seconds. So again, however long it takes for it to repeat one full cycle. Part C, the sine function. This is our general sine function of x. So we know from our unit circle that sine, and if you need a visual, sine is the y value, remember. So here, the sine of 0 is 0. Sine of 90 degrees is 1. Sine of 180 is 0. Sine of 270 is -1. And then back here at 360, we see the repeat start. So that's how we know that the sine function has a period of 360 degrees, or if we're in radians, we would say it has a period of 2 pi. Part D, a radar line takes 1 second to travel through 1 radian. So this one's a little bit trickier, but think about that radar, think about that radar screen. It's a circle, and it takes that, this problem is saying that it takes the radar line, which is the radius, 1 second to travel through 1 radian. So we know 1 radian is about there. That repeat for the radar screen doesn't take place until it gets all the way back around. So if it takes 1 second for 1 radian, we know that there are 2 pi radians around that whole circle, which means that period is 2 pi radians as well, or 2 pi seconds. Okay, so we're going to move on now to 2.2.3. The purpose of this problem we just did is so that you can see there are times that the sine function will be stretched out, and what that means in terms of formal language is that the period of the sine function can be altered. So now I want you guys to pause and make sure you have that 9.2.3 worksheet in front of you. This is not going to be guided notes through this video, so you guys are going to be working through this by yourselves at your tables. But I do want to clarify a few things and show one example for you. So go ahead and make sure you have that out before you continue the video. Okay, so if you haven't yet turned to page 469, this is going to walk you through. You will need your books for sure on this one because I haven't written out every problem on this worksheet. I'm actually going to jump to problem 117 because I want to clarify how you guys will need to make sure your windows and your calculators look, and also what I'm asking for, what each of these parts is asking for you to do. So first of all, you need to think about domain and range when we're talking about the sine function. So in this, when it says write down what you're using for your window, first of all, we are going to be in radians. So the first thing you guys need to do is make sure you're in radians, which means we are talking about repeating here over at 2 pi. So our x max, which is typically 0 to 360 if we're in degrees, we're now going to use an x minimum of 0 and an x maximum of 2 pi. So make sure you guys know where that pi button is, which is just underneath the clear button on your calculator, but you'll need to hit second first. The y minimum and the y max, remember that the sine function never exceeds +1 or gets lower than -1. So the y minimum would be -1, the y max is +1. So you need to just hit your window button now, make sure that you have set up your min and max for your x and y's correctly so that when you look at the screen, you are looking at a good window. So let's do B together, and then you guys will, at your tables, continue through this lesson independently. So on part B in 117, it's asking to graph. First of all, step 1 is graph each of these. So I expect you to need your calculator at this point for graphing these, so you can type it into your calculator and sketch the graph. So the sine function, we are getting used to doing this over and over here. So we know it's 0 at 0, pi, and 2 pi. At pi halves, it's +1, so you'll need to label this y-axis with -1 and +1, and then we can graph it. So this is just one cycle of the sine function, so my arrows indicate that will continue. Okay, so let's look at the book, and that part I, the first part there, is asking how many cycles of the graph appears on the screen. In our screen, which goes from 0 to 2 pi, only one cycle of sine of x appears. But this will change as you look at the other ones. So when you graph sine of 0.5x, your answer for how many cycles appears will change. Part 2 is asking the midline. That's the horizontal line of the graph. So it's the graph that or the line that it's asking for the equation of the line that's in the middle of that. So that equation is just y equals 0. Part 3 is asking for the amplitude. Remember, the amplitude is how high or low it's getting, not the total height from the highest to the lowest, but the distance from those peaks or valleys to the midline. So this has an amplitude of 1. Part 4 is asking for the period of this function. We know now that the period of a function is how long it takes to repeat one cycle. We see that repeat start here at 2 pi. So this would be, I'm just going to use p, 2 pi. Again, this will change. So I'm going to put little stars next to the ones that will change with each new equation. Part 5, does this equation represent a function? Yes, it does. So you can think of that in terms of the vertical line test or just the number of outputs for each input. Okay, so what you guys are going to continue doing is graphing these other 4 equations. You can see the slight change on the equation, and we're going to look at how that affects the graph. What I expect you guys to do moving forward, since I'm not here to answer questions or talk you through anything, make your best attempt as a group, make sure you're working together to answer these questions moving forward. So again, when you look at 117, continued, answer the questions as you can, and then as you finish each part, go up and check my answer key. The purpose of this is not to quickly scribble down the correct answer. It's not important to get the correct answer down as much as it is that you guys are understanding the content as best as you can. With 15 minutes left in the class, I want everybody to move on to problem 119, regardless of where you are. This final problem, 119, summarizes transformations on the function on sine, and that impact that our new parameter right here in front of x. So we see, let me outline this again so you can see, like this 2 out front here. This 3 out here, that's not the value affecting the horizontal shift. Remember, that's the value of A that would affect amplitude. So I will undo that one. But we have this one here, this one here. So those are going to affect the period, and that's the goal here. So you guys are going to be analyzing each of these functions to talk about amplitude, period, horizontal, vertical, and then you're going to match it to the graph. So once you figure out all of these 4 things, then you should be able to figure out which graph will match up with it. Just as a quick reminder here, the amplitude in our equation is A, period was the value of B that we just introduced. Horizontal shift is that value of H, and then that vertical shift was, H, and then K. So that's what we're trying to identify in each of these and then match them up with the graphs. Again, make sure you have at least 15 minutes at the end of class to work through this as a group and check your answer. And we'll pick up, hopefully I'll be back next class so I can answer any questions you have on this.